just to keep it a little bit more informal. Okay, so the stream is on. The recording is on. All right, so let me just start by having a quick introduction. Sorry, someone is calling me. Okay, whatever. Sorry, I was. Yeah, my pocket was vibrating, so.
Yeah.
All right. Sorry about that. All right. So yeah. So thanks, Amir. Thanks very much for taking the time to keep this presentation on a topic that is really exciting. So Amir is a PhD candidate at the University of Sussex, and his ultimate goal after getting his PhD will be to continue working on research, either in academia or for companies. So if anyone is listening and wants to hire Amir, snap him up before he gets hired by some evil corporation. Anyway, so yeah, he's going to talk about system. So the title of his talk is Systematic Analysis of Programming Languages and Their Execution Environments for Spectre Attacks. You can see this joint work with a number of people in Austria, Portugal, London, and so on. So without further ado, thanks a lot, Amir. Take it away.
Yeah, thank you so much. So actually, yeah, the work is a result of a work that I was doing as a visiting researcher at TU Graz in Austria. As the title suggests, the work is specifically on Spectre attacks, and we want to see, or it's better to say, we want to analyze programming languages and execution environments against Spectre attacks. I'll first give like a gentle introduction and then go through the background, specifically speculative execution and transient execution attacks. And then I'll talk about gadgets a little bit more to be able to understand Spectre. And then I'll try to quickly take a look at program executions and the way that we can we have categorized them in the paper. And we take a look at the feasibility of attacks in documentation and also in practice. But to be able to take a look at them in practice, we need to take a look at Speconnector, or the tool that we developed just to make our lives easier with the analysis of attacks in practice. And then we take a look at two case studies and finally the conclusion. So what was the problem? Or let's say, what was the research question? What did we want? What did we say that? What did we see that is missing, and which we were trying to address? So we know that Spectre mitigations mainly are on the operating system level, or sometimes in the execution environment level, and also we know that. There are like tons of mitigations since the Spectre was introduced. There've been like tons of different work that they were trying to address Spectre and trying to mitigate it. Also, we have like a large number of programming languages and the execution environments. The problem is that it was not clear that which programming language and which specifically execution environment have like a practical and efficient mitigation against which kind or which variant of Spectre attack. So we try to take a look at the top 30 programming languages and which resulted in the analysis of 42 execution environments, because for some programming languages we've got like a couple of different execution environments. What we did was that we analyzed the security of the execution environments against Spectre, And we introduced Speconnector, which is a novel tool. It's there to evaluate and exploit Spectre gadgets, and the main property or the main characteristic of it is that it works independent of the target programming language. We'll talk about it like a little bit later, a little bit more. Also, it demonstrated the security impacts of two crypto libraries using using Speconnector, and we kind of concluded that it could have been like mitigated using using a mitigation on the compiler level. For the background, so we have out of order execution, and we have a specific kind of it called speculative execution. We know that when we run programs and they've got, like, for example, conditional branching, if we have some conditions that they need to take a little bit more time to be evaluated, then the CPU cannot afford losing a lot of time just to wait and kind of just wait for the result of that. For example, if we have some parts which are in the condition that are they're not in the cache, they're like in the memory, we need to cache them and then use them. Calling them from the memory takes a longer time for sure. So, but the problem is that we can't just wait there and do nothing. What CPUs do, they've got some policies to execute them to predict the the direction that is more possible or more probable to be happened, and then go through that path. And this is called speculative execution. And if the prediction is not correct, then the CPU would roll back the architectural state. If it's correct, we're good to go. But if it's not, it rolls back the architectural state. But the problem is that it does not take microarchitectural state into account, and it does not revert it, it does not roll it back. And that is where transient execution attacks or specifically like Spectre comes from. Since the microarchitectural state stays the same, we can reconstruct the architectural state and bring the information from that level up there and kind of reconstruct them. And normally, or it's better to say traditionally, we're using side channel attacks to reconstruct this state. And to be able to do that, we need a piece of code, which we call it a gadget. In the sense of Spectre, we've got gadgets for different types of Spectre, for different variants of Spectre. What we're trying to do in this part, in this slide, is that we're going to take a look at index gadgets, which is an example of the Spectre version 1 or variant 1. Which takes advantage of the pattern history table, PHT. Take a look at the code over here. We've got a variable x, which is of the attacker's control. We've got the length of data, the array data, and we've got another array data. The array data belongs to the victim, and it's in the address space of the victim. The lookup table is a shared memory between victim and the attacker. So if we try to run this code, run this piece of code in our program, imagine that we run it 1,000,000 times, and every single time x is less than the length of data. So we know that it's valid and data can access, we can access it, and we can load x. And we can load data x and then use the index, multiply it by 4,096, and kind of load the lookup table of that index and do something with it. But what would happen if a length of data is not in the cache, it's in the memory? After running it 1,000,000 times that x is less than that, suddenly it's not in the cache, it's in the memory. We need to fetch it from the memory, but we need to kind of guess as well. We need to kind of predict as well based on what we've done during like the history of 1,000,000 times. We've always, I mean, the x has always been like greater than, less than the length of the array, so we can access it. So the CPU speculatively executes this part, but what if x is greater than length of data? We don't have any check on x, we're running it, and suddenly we just go beyond the length of data and access to some other parts of the victim's memory. And we just load some information into lookup table, and lookup table index something is now inside the cache. So CPU understands that, okay, x is greater than that, and then rolls back everything, but still lookup table of an index is inside the cache, which we can then go and check which index of lookup table is inside the cache, and then understand what was the character that part of the memory was kind of taking a look at it. I can go through this like a little bit deeper, but if you got any questions about that, let's just continue a little bit more to understand it a little bit better. So with regards to now let's take a look at the program executions. We talked about Spectre. Now let's talk about like the other parts. We categorize the execution environments into 3 different categories. And the way that we kind of consider the categories is the way that we execute the program. We consider them as interpreted program execution, as compiled program execution, and as managed program execution. Please also consider that this categorization is kind of it's like an orthogonal problem, or it's like an orthogonal, it's orthogonal to the choice of the programming language that we want to have. Because we know that like we can like interpret or compile or like hybrid or have a hybrid compiler for any programming language. It's just the way that we categorize them. It's just a matter of like the commonly used compilers or interpreters for different programming languages. And from now on, we are trying to we actually address them. The programming languages that are using interpreters commonly, we address them as interpreter languages, and the same with the compiled and managed languages. So with regard to interpreted languages, we need to translate them every time they're being run, but this gives us the portability of the program as well. We can just take the program and run it anywhere as far as the interpreter is like installed on that is like there on that platform. And the it's like a kind of way that we interpret them is showed in the figure. We have the source program, we interpret it during the runtime. We kind of use the input data, we get the output, and everything is done during the runtime. With regard to compiled languages, they actually face the overhead of translation only once. And therefore, we can have like a better optimizations since we're just compiling them once. We can have like a more sophisticated and better optimizations within the translation, within the compilation part, and then run them. So we compile them, we get like an executable file, and we run that for as many times as we want to. And with regard to managed program execution or managed languages, we're trying to kind of get the advantages of both interpreters and compilers. So what we try, and also like there are like a vast variety of like these managed program executions, but we just showed 2 of them. One example which includes the OCaml, which OCaml compiler is working that way. It's called OCaml C, OCaml run. We have the compiler generates a program independent code. And in this phase, we can do the optimizations that we want. And also we can have the portability by running it in the interpreter as many times as we want to. And also we can have it in the way that, like, for example, JDK Java compiler has it. Like we have a compiler which generates a platform independent code, and then we inject that to a JIT compiler. JIT compiler produces an executable file which would be interpreted by the interpreter, and then it gives feedback to the JIT compiler, and then again and again we have the loop to for the execution in the runtime. So that was like the background for Spectre and also for the program execution. Now let's take a look at the feasibility of attacks in documentations, and it's better to say in theory or in documentations. With regard to interpreted languages, we studied 9 different interpreters and 9 different languages. We looked into the publicly available documents for each and every case, and by publicly available documents, I mean like whatever they have online, like or we could find online based on their documentations, or if they've got any repositories. We try to like take a look at them and gather information in this phase, and for some reasons, for several interpreters, we're not able to find any information. And as an additional source for our studies, we kind of contacted developers of the interpreters to get some information about like the interpreters from them by direct communications. But again, unfortunately, we're not able to gather information for 8 out of 9 interpreters. So for all interpreters except for Perl, we were not able to find any information, and crosses show that. The crosses in the table show that. And for Perl, we figured that there is no mitigations available against any of the Spectre variants, and a square with a cross in it shows that as well in the table. The next one is compiled languages. We took a look at 15 different compilers in this work, and we kind of followed the same approach that we did in the previous case. We took a look at publicly available documentations, and we also took a look at the we also contacted the developers as well, and we gathered information that way. Based on the analysis that we got, the Go compiler had like kind of the best situation regarding the information and the mitigations between the cases that we were able to analyze. As you can see, this is the result of the analysis that you can find in the paper as well. The next one was about managed languages. We analyzed 13 different programming languages and subsequently 18 hybrid compilers. And we kind of did like the same way, we kind of followed the same way that we did the analysis in the previous parts. And surprisingly, we figured that for the majority of cases, they either didn't have any mitigations implemented or didn't have any information about the mitigations that they implemented. And this is the result that we got in this phase of the work. As you can see, the majority of them, they have crosses and all like crosses in a square, which says that there's no mitigation, or they have, or in the cases that there are mitigations, we have a tick inside the square. And also you can find these tables in a more in a better way, actually, inside the inside the paper itself, and because it's a bit more expressive inside the paper as well. Let's now, before actually moving to the practical analysis, let's take a look at the tool, which is called Speconnector. The threat model for Speconnector is the regular Spectre attack threat models. We have an attacker, which is a co-located program, and it's running under the same OS. The attacker is able to execute arbitrary code on the victim side, and the victim has an interface that like the attacker can interact with. We know that the possibility of the attack to be successful depends on whether or not the victim has a leakage of information. Because if it doesn't, then the attack is not going to happen. And for that purpose, we focus on the data leakage rather than focusing on the engineering side of the work. And we use Speconnector for this purpose. Once the Speconnector finds the leakage, having like a kind of attack in a very specific way for the program language, which is implemented completely inside that program language, is just a matter of engineering, and it's just a matter of like basically engineering and like having a code inside that target language. And the method that we used for the Speconnector, so that we'd be able to have it independent of the target language, is in the following way. The target code first allocates 256 pages of memory. These 256 are basically for the ASCII code with the length of we've got 256 characters. The target code then fills the allocated memory with a non-magic value that we've got, and fills the 256 pages. Now Speconnector also allocates the same amount of memory, and it actually uses the process information so that we can get the page frame numbers and then set the page frame numbers in our program, so that we can kind of have a shared memory between the attacker and the victim. And once the victim accesses one of the pages inside the memory, inside this program, and inside the gadget that we mentioned, we can retrieve it on the attacker side by a flush and reload, and check like basically which page was accessed during the running of victim. And that's pretty much the method that Speconnector is using. And with regard to that, the attacker is inside is a C program that is running, and the victim and the gadgets, the victim code which contains the gadgets can be in any program languages, and the attacker is like independent, and the code is independent of the victim language. So using Speconnector, we took a look at interpreted languages, and we are able to exploit Perl against Spectre attack and kind of retrieve the information. A potential explanation for the other cases that did not happen and we were not able to do it is actually that maybe the speculation window is like a little bit too small, so that we can like fit the attack in it. And this is a table for the result. That none of the attacks kind of depended on the setting of the compiler or the interpreter in this case. And we were able to find cover channels, but we were not able to find or pull off the attack. The next one was for compiled languages. We're able to establish a cover channel in 14 of them, and also 12 of them were generating a code that was vulnerable to Spectre attack, or at least a variant of it. And this is the table that we got. In some of the cases, we needed to kind of take a look at the settings as well and change the settings of the compiler, but in some of them we didn't. As you can see, for example, OCaml ops is the compiler for OCaml language, and we have a JIT compiler for it, sorry, not JIT compiler, we have a managed compiler for OCaml as well. And for the managed languages, we're able to kind of demonstrate a cover channel in all of them. And we actually introduced like attacks for several languages which were previously not known to be vulnerable against Spectre. These languages are or include Dart, Java, C#, Scala, Groovy, Kotlin, and OCaml, specifically OCaml C and OCaml Run managed compilers or hybrid compilers. And the table is as follows. Now let's take a quick look at the case studies for this for these for the analysis that we did. So we took two different case studies to kind of see how they leak the information, or if they leak the information. We found the first one is Alice, which is a crypto library which is kind of operating the AES encryption, and it's written in Java. And the second one is a well-known crypto library. It's called CryptoKit, and it's written in OCaml. In both cases, we're able to retrieve the secret, and we also argued that the mitigate and that if we had a mitigation in the compiler level, we're able to prevent the attacks from happening. And also, we can see that both cases were in between the vulnerable cases from the previous section that we mentioned, and they were like in the table. We actually found them vulnerable before the case studies. Finally, we did a systematic analysis of different program languages and also their respective execution environments against Spectre attack, or and we analyzed them in both theory and practice. And for the practical analysis, we use Speconnector to be able to like have the attack and run it independent, and kind of run the attack and kind of analyze it independent of the language of the gadget. And we showed Spectre. We showed like kind of Spectre attacks in 8 new program languages, or in 8 program languages that were not known as vulnerable languages against Spectre attacks, or against each of the variants of the Spectre attacks. And also, we kind of showed it in 2 case studies. Thank you so much for your attention. In case you got any questions, I'll be happy to have a conversation about that.
Awesome. Thank you. Thank you.
Oh, thank you.
So let me just check if there is any question from the YouTube chat. Just a second. Let's see. No, I don't see any. There is a bunch of spam, but yeah, no. Okay, so I guess I can stop the recording.